Okay, welcome back to the series of lectures on transform calculus, and so far we have covered Laplace transform, including its applications to solving partial differential equations, ordinary differential equations, and in the rest of this lecture we shall discuss about the Fourier transform. And before we continue this Fourier transform, it is very important to introduce Fourier series, because it gives a pathway to understanding Fourier transform. And Fourier series has its own wide range of applications, for example, in analysis of current flow and sound waves and many more. They are also used to solve differential equations, and in a general sense we can say that we use Fourier series to represent or to approximate a periodic function, and indeed not a periodic function, but a function which is defined on a finite interval. So, let us see that if a function is defined, for example, in a interval 0 to L. So, what we do in that case, since this Fourier series represents a periodic function, that we extend this as a periodic function on the whole real axis, and then we approximate this function which is periodic now by the Fourier series, and then this Fourier series will approximate this function which was defined 0 to L. So, in that way we basically can have this Fourier series for any function which is defined on a finite interval 0 to L. So, since we will be talking about the periodic function, so let us again we just recall this. So, if a function f is periodic with period t, then we have f t is equal to f t plus this period. So, the function value is again the same after this period capital T, and the smallest of t for which the equality holds, or which for which the equality f t is f t plus t is true, is usually called period of f t. So, most familiar periodic functions are like we know already, the sin x, cos x, tan x, and so on. So, the one point here, or the property of these periodic functions, that the sum, difference, or product, or the quotient of two periodic function is again a periodic function. So, consider for example, a function f x as sin x plus sin 2 x plus cos 3 x. So, what is the period of this sin x? Is 2 pi. The period of the sin 2 x is 2 pi divided by 2, and the period of this cos 3 x is 2 pi and divided by this frequency 3. So, we have 2 pi by 3, that is the period of this function. So, what we see that the common period of all these three functions is this 2 pi. It has two circles in this 2 pi range, it has 3 circles or cycles in this 2 pi range. So, the common period is basically 2 pi of this function, and basically what we have, that f x plus 2 pi will be, so because f x plus 2 pi is again sin x, and sin 2 x plus 2 pi will be again sin 2 x, because this 2 pi is also period for this sin 2 x function, and same for this cos 3 x. We have again this the value will repeat after this 2 pi. So, we have this common period for all these three functions is 2 pi, and that is the period of this f x function. So, f x is periodic and it has the period 2 pi. So, let me just introduce an interesting property of periodic function, which we shall be using in this lecture. Periodic functions, a property of periodic function. So, if we have a periodic function of period capital T, then and the function is integrable. So, a to t plus a. So, we are integrating over this length t, this function f t, which is a periodic function of period this capital T. So, this will be equal to, we take any other b here and b to b plus t f x dx for any a and b. So, if a function is integrable on any interval of length t, then this is integrable on any other interval of the same length, and the value of the integral is the same. And this we can, without going to formal proof, what we can see, here, that for example, we consider that this is the periodic function we are talking about, and so on. So, this is from 0 to capital T, we have this period, and so on. So, if we integrate, for example, from here in a interval of this t, so this will end up here, this is again t. Now, if you see that this area which we get after this integral is basically equal to this area if we integrate over 0 to t. So, basically what we have, that 0 to t f x dx, 0 to t f x dx, this is equal to any a we can take up to a plus t as we have taken here, and this will be equal, because the part we left here of this smaller circle, that is included here. So, we are getting actually this area. So, this result is true. Now, we talk about the trigonometric polynomial and trigonometric series. Trigonometric polynomials and series. So, trigonometric polynomial of order n is defined, I will call it S n x, some constant plus k from 1 to n, another constant a k, and cos k pi x over L plus b k, and sin k pi x over L. So, what is the common period of these functions here? So, the common period, the largest period what we will get while putting k is equal to 1. So, this is, we will get here cos pi x over L and this sin pi x over L, and here the period is 2 pi over this number pi and L. So, we have 2 L. So, what this represents, this sum, this represents a function of period 2 L. However, if we keep on increasing this n, this will still represent a function of period 2 L. In fact, the result is true for the infinite series as well, if it converges, of course. So, the infinite series, if we talk about a plus this k from 1 to infinity, a k cos pi k x over L plus b k and sin pi k x over L, if it converges. So, if it converges, also represents a function of period 2 L. Now, the question is, can any function, can any given function of period 2 L be represented as a sum of trigonometric series? And the answer to this question is yes, because it is possible for a wide variety of or wide class of functions. So, we will be talking about today that how to get such a infinite series for a given function. So, before we go into that detail, we just consider the orthogonality property or conditions for the sine and cosine functions. So, we call two functions phi x and psi x orthogonal on the interval a to b if a to b phi x psi x, if this integral is 0. And with this definition, what we can say that the basic trigonometric system, of period 2 pi. So, 1 cos x sin x cos 2 x sin 2 x and so on, cos n x sin n x is orthogonal on the interval minus pi to pi. So, we shall prove that any two distinct functions, if we take, then they are orthogonal. So, let us go through the proof quickly. So, for any integer, if we take which is not is equal to 0, what we have that minus pi to pi, if with this function 1 we take any other function cos n x dx, what will be the integral? This is sin n x and over n, and we have minus pi 2 pi and sin n pi 0, sin minus n pi is 0. So, we get here equal to 0. Similarly, if we take here the multiplication with 1 and the sin n x for any n not equal to 0, because for 0 it is going to be 0. So, what we have here minus cos n x over n and minus pi to pi, and this cos n pi will be minus 1 power n, and again this cos minus pi will be the same, minus 1 power n. So, here this will also give us 0. Let us see what will happen if we take the same functions from that system, that means minus pi to pi, and if we take cos square n x. So, cos n x and cos n x, the product. So, minus pi to pi, and we have this 1 plus cos 2 n x over 2 dx, and in this case, so this will give 0 because sin 2 n x and pi and minus pi both will be 0, but we have here half and the integral, that is 2 pi. So, we get pi, and similarly if we take the sin n x and sin n x, so sin square n x dx, we will also get this pi because we have 1 minus cos 2 n x over 2 dx, and this will also give then pi. Now, we take for any integer m and n, where m is not is equal to n, what we have if we integrate minus pi to pi and cos n x and cos m x. So, any two function we have taken here. So, what we can write this 2 cos n x cos m x. So, minus pi to pi, that will be cos n x plus m x. So, n plus m x n plus cos n x minus n m x. So, n minus m x and then dx. So, again we have sine after this integration, here also we have sine. So, in that case this pi and minus pi both will give us 0 again. And similarly, if we take here sin n x and sin m x, the product of these two functions, and we can again see that this will be also 0. So, 2 times this will be cos n x minus m x. So, n minus m x and minus cos, the sum of these two. So, this is n plus m x dx, and for the same reason we have also this is equal to 0. Now, we take the left combination, and that is again for any integer we can take m and n, and if we take the product of sine and cosine, so n x and the cos m x dx. So, in this case we have minus pi to pi sine n plus m x and 2 sine cos. So, we have plus this sine a minus b. So, n minus m x and dx, we will get here cos, and cos pi or minus pi, it is the same value. So, we will get again 0. So, in brief, what we got for any integer m and n, we have the following result, that from minus pi to pi, if we integrate this cos n x cos m x dx, or it is a property of the periodic function that instead of this minus pi to pi, we can go for any a to a plus 2 pi, it will be the same. We have cos n x and cos m x dx, and this will be 0 if m is not is equal to n, and will be pi if m is equal to n, because in that case we have the square here, and of course, these should not be equal to 0, otherwise we will have 2 pi value here. So, this is one result we have. The second one, minus pi to pi, if we take sine m x or n x m x or a to a plus 2 pi, the same value we will get n x and sine m x dx. In this case also we have this 0 if m is not is equal to n, and we have pi if we have m is equal to n and not is equal to 0. So, the last case we have minus pi to pi, where we have combination. So, sin n x and cos m x dx, this will be a to a plus 2 pi, and we have sin n x cos m x dx, and this is always 0, whatever is m is equal to n or not equal to n, we will get 0. So, this was for the family or for the system where the common period was 2 pi and we are integrating from minus pi to pi. A similar result we have basically more general for the system. If we take 1 cos pi x over L sin pi x over L cos 2 pi x over L and sin 2 pi x over L and so on. So, here the common period is 2 L, and now we have again a similar result, that if we integrate from minus L to L or from 0 a to 2 L or 0 to 2 L. So, we have cos m pi x over L and cos n pi x over L dx, or we take this from a to a plus 2 L the same integrand, and this will be equal to 0 if m is not is equal to n, and will give us L if m is equal to n and not is equal to 0. The analogously we have this second result minus L to L, and we have sin m pi x over L and sin n pi x over L dx, or a to a plus 2 L we can integrate. So, if m is not is equal to n, otherwise it is L if this m is equal to n and not equal to 0. And the last one, if we have the product of the two, that sin m pi x over L and cos n pi x over L dx, and this will be 0. So, now we have done this preparation to go for the Fourier series. So, Fourier series now we will introduce, and here so we let us start with, so let f x be defined in the interval minus pi to pi and as 2 pi periodic. So, let me just mention this, that for simplicity we are taking the symmetric interval, but definitely this is not necessary at all, that all these functions to be defined on a symmetric interval. So, this is just for the simplicity, and later we will see while discussing the examples that we will go for basically for any interval, but the function should be periodic. Or later on for the Fourier series also we will generalize this when the period is not 2 pi, but for any given general period what will be the Fourier series. So, now suppose the function f x has the expansion f x a naught by 2 k 1 to infinity a k cos k x b k sin k x. So, we have taken this instead of this constant a naught by 2 to have this consistency with this a k. Later on we will see why this factor 2 we have introduced here. So, now the question is, or the problem is, that how to determine these coefficients for a given function f x. Yeah, so for this we have taken one assumption that the series here can be integrated term by term. That is, we have assumed that for the series the integral of the sum is equal to the sum of the integral. So, now we integrate the series here from minus pi to pi for a general case when we will be taking minus L to L for the function of period 2L, we will integrate again from minus L to L, but in this case we integrate this minus pi to pi, and let us assume that the integral of this is equal to the integral of this f x. So, integrating the series 1 from minus pi to pi, what we obtain minus pi to pi f x dx. So, this is a by 2 and the integral minus pi to pi, and we have 1 dx and plus k 1 to infinity, we have here a k and then minus pi to pi cos k x dx plus this b k, and we have this integral minus pi to pi sin k x dx. So, both these integrals, this one is 0 and the other one, both are 0, we have just seen. So, what we get from here, that a naught, because this will be 2 pi, this is 2 pi. So, we have a naught pi. So, a naught is 1 over pi and minus pi 2 pi f x dx. So, we have obtained this a naught, the one coefficient of that series, and now we multiply to get the other constants. So, we multiply 1, that series 1, both the sides, so to f x and the series. So, both the sides by cos n x and integrate. So, from minus pi to pi, of course. So, what will happen in this case, we have minus pi to pi and f x cos n x dx is a naught by 2, we have minus pi to pi and cos n x dx plus k 1 to infinity a k minus pi to pi cos k x cos n x dx and plus b k minus pi to pi sin k x. So, sin k x and cos n x dx. Okay, so this is the sin and cos. So, this will be always 0, that is what we have seen, and here we have cos k x cos n x. So, when this k will be n, this value would be pi for k is equal to n, and the rest all the values are 0, and this is again this is 0. So, what we got, that minus pi to pi and f x cos n x dx is equal to, we have this a n and pi. So, we get basically a n is equal to 1 over pi minus pi to pi and f x cos n x dx. So, this is the formula for the a n, and here n is a 0 we already got, but if you see that a 0 now we have this, we can also get from here, because a 0 is going to be 1 over pi minus pi to pi f x dx. So, this is basically true for n 0, 1, 2 and so on. And similarly, we can get this b n. So, we multiply instead of this cos n x by sin n x, and in that case this term will vanish, and here we will get pi, because sin k x sin n x. So, in this case b n we will get 1 over pi minus pi to pi f x and sin n x dx. So, here the n are 1, 2 and so on. So, these coefficients, the a n and b n, they are called, so this a n and b n, they are called Fourier coefficients, and the trigonometric series, this a naught by 2 and this k 1 to infinity a k cos k x plus b k sin k x is called the Fourier series. And we normally denote by this tilde. So, f x, this is the Fourier series for f x, and we are not writing here the equality, because first of all this is clear from the construction. We have evaluated these coefficients a k and b k by putting the integral equals, and that does not mean that the f x is equal to the sum of the series. So, that part we will be discussing more in detail, that when we can have the equality, that means the series converges to the function value f x. Okay, so, just a remark here. So, if we just take a look at the coefficients, this Fourier coefficients a n and b n, this is minus pi to pi f x cos n x dx, and if we change the value of the function at finite number of points for this f x at finite number of points, then these integrals defining these coefficients are unchanged. So, the functions which differ at finitely many points have exactly the same Fourier series. Okay, so, this was the Fourier series for the function of period 2 pi, and we have defined, or we have assumed for simplicity, that our function is defined from minus pi to pi. And now we go for a general case. We will skip definitely the proof, because all the steps are very similar what we have done, but now we will consider when a function is of a general period, and we let us say 2 L again for simplicity, and define in the interval minus L to L. So, let f x be defined in the interval minus L to L, and f x is 2 L periodic, then the Fourier series of this function will be given by a naught by 2 k 1 to infinity, and we have to take now the family of the trigonometric function which has the common period 2 L. So, that will be cos k pi x over L plus b k and sin k pi x over L, and where these Fourier coefficients will be given by 1 over L. So, instead of 1 over pi, we have 1 over L and minus L to L f x, and these functions k pi x over L dx, or we can also integrate from a to a plus 2 L, that integral value will be same. So, for the bk we have 1 over L minus L to L, or from 0 to 2L, or a to a plus 2L, this f x sin k pi x over L dx. So, this is the general Fourier series where a function is of period 2L. Now, we have the following questions to be answered. So, does the Fourier series converge at a point x minus pi to pi, or if the series converges at x, is the sum function equal to f x? So, the answer to these questions are in negative, and there are functions defined on minus pi to pi whose Fourier series diverges everywhere, and there are functions in fact continuous functions whose Fourier series diverges at a countable number of points. But we are not going into the detail of all these convergence and the conditions for the different kind of convergence, but because this is a rather introductory lecture and we should go to this Fourier transform later on. So, what we do, but let me just mention that we definitely have some additional conditions on this f to ensure that the series converges, and that we will see in a minute. But before, let me just mention that there are several notions of convergence, and the one is the pointwise convergence, which we will be talking about, pointwise convergence. So, in a rather informal manner, if I define here, so consider an infinite series, f 1 x plus f 2 x plus f 3 x and so on, or we can write in summation form k 1 to infinity and f k x, and such a series is said to be convergent for a given value of x if its partial sum S n x, which is n or k is equal to 1 to n, and f k x has a sequence of partial sums have a finite limit, that is the limit n tending to infinity S n x exists, and let us call it that this is equal to S x. So, if this is the case that for a given value of x, this a sequence of these partial sums S n x converges to some S x, then we call that we have here the pointwise convergence, because it is depending on a particular value of x. We have a stronger version of convergence, and that is called uniform convergence. And in the uniform convergence, a sequence this f n of functions converges uniformly. So, this is the stronger notion of convergence than the pointwise convergence, uniformly to a function, a limiting function f, if the speed of convergence of this f n x to f does not depend on x. So, what does that mean, the speed of convergence? That a little bit with the help of examples we will see. So, if we just take an example, f n x is equal to x power n, it is a very standard example, and x is between 0 and 1. So, this function will converge pointwise to a function f x, which is 0 and 1, 0 when x is 0 and 1 in the open interval, and when x is equal to 1. So, let us see what is happening here. So, if we take any x between 0 and 1, this x power n, as n approaches to infinity, will always go to 0, and if we take x is equal to 1, so then in fact it is 1. So, we have this 1, it is a constant sequence in that case. So, now we were talking about the speed of convergence, that for the uniform convergence, the speed of convergence of this f n x does not depend on x. So, what is happening here, that if x is close to 1, for example, if x is close to 1, then this convergence is very slow, because we have very close to 1 power n, and this sequence will go slowly to this 0, and if we have x close to 1, this will go, or this will converge very fast to this 0. So, what we see here, that this convergence, the speed of convergence varies with this x. But for example, if we take a function sequence of function 1 over n and sin n x, and for basically any x we can talk about, and this will always go to the function f x is equal to 0, and here we have uniform convergence, and of course, the pointwise convergence, because this is a stronger version of the convergence. So, in this case, whatever x we take, 1 over n will go to 0, and it basically does not depend on x, but here it was different. If x is close to 1, then we have a very slow convergence to 0, but in this case we have 1 over n here, and whatever x we take, I mean, we can avoid the case of 0, then it is a constant sequence. So, that is of course 0, but in general, I mean, this is not depending on x. Yeah. So, we are not going into very much into the detail of these two notions of convergence, but I hope that I have given at least some idea of the uniform convergence and also for the pointwise convergence. So, now we can talk about the convergence theorem. Convergence theorem, or this is also called Dirichlet's theorem, and these are the sufficient conditions for the convergence. So, what we have, suppose that the f x is defined except possibly at a finite number of points in, and let us take a general interval. So, minus L to L, or we can take an open interval minus L to L, and the f x is periodic with a period 2L, and f x is piecewise continuous. So, we have already defined this piecewise continuity. So, the function is continuous other than some at finitely many points, and at those points the right and the left limit exist. And the one more condition here we need, that one-sided derivatives of f exist and is finite. So, and is finite at each point in this minus L to L. So, what does that mean, one sided derivative? So, we have the limit h to 0 from the positive side. So, f x plus h, this is right derivative, minus f x, the right limit of this function at x. The function may not be defined at x. So, we have divide by h if this exists and is finite, of course, at each x minus L to L, L here the closed interval, and the left limit h to 0 minus or 0 plus, sorry. So, f x, the left limit, minus f x minus h over h, this exists at each x minus L to L. Here we have, so here we are talking about the right limit. So, when we are here that f x plus, so basically this here it should be the open interval, the right side, because here we take we exclude the case because at this point L we do not require this right derivative to exist, and here at this left point minus L also we do not require that left derivative to exist. So, at all other points both the right and the left limit should exist. At the extreme left end only the right limit, the right derivative, and at extreme left only the left limit or left derivative should exist. So, what we have these conditions, that if f x is defined except possibly at a finite number of points, and the conditions that if f x is periodic, piecewise continuous, and these one sided derivatives of f exist at each point in minus L to L. If these conditions are satisfied and these are the sufficient conditions for the convergence, then for each x minus L to L, the Fourier series a naught by 2 plus n 1 to infinity a n cos n pi x over L and this b n sin n pi x over L converges to f x plus minus f x minus divided by 2. So, to the average value, and note that. So, in that case this is equal to this basically, and at the point of continuity, because this right limit and the left limit they are equal to f x, plus this is the average value. So, at the point of continuity this f x plus is equal to f x and this f x minus is also equal to f x. So, in that case we have this equal to f x at the point of continuity. Otherwise, we need to take the average value to make this equal. And the last remark, what we have, that in addition to all these assumptions what we have, if our function is continuous, then we have even a stronger version of this convergence, and that is the uniform convergence. So, but we are not going into the detail of all these convergence. So, let us just quickly go through the one example. So, find the Fourier series of the function minus pi x, and we have minus pi when x is minus pi to 0 and x is 0 to 2 pi, and the function is periodic. So, f x plus 2 pi is equal to f x, and further, so here find the Fourier series to represent the function which is defined by this, and the further find the sum of the series for x is equal to 0 and x is equal to plus minus pi. So, this function, if we just take a look, it's x when 0 to pi, and it's minus pi and 0 to minus pi, and then it's periodic. Okay. So, then we have again here, and it will go like this. So, the function is periodic. So, this and all other conditions are of course satisfied, that it's piecewise continuous and the derivative at all these points, left and right derivative exists. So, we do not have to check that. So, this is the Fourier series cos n x plus b n sin n x, and we calculate this a 0 first, that is 1 over pi, and we have minus pi to pi f x dx. So, f x dx. So, we can break this from minus pi to 0, we have minus pi dx plus 0 to pi, we have x dx, and this is 1 over pi and minus pi square, because minus pi and then we have x here. So, we will get again minus pi. So, this was minus pi square and plus we will get pi square by 2. And this is nothing else but pi by minus pi by 2. Now, we calculate the a n for this function, a n 1 over pi minus pi to pi and f x cos n x dx. We have 1 over pi minus pi to 0 minus pi cos n x dx plus 0 to pi, and the function is f x cos n x dx. So, 1 over pi, here we take minus pi, and this is sin n x over n minus pi to 0 plus 1 over pi, this 1 over pi, and we have to integrate by parts. So, we have x and sin n x over n 0 to pi minus 0 to pi and sin n x over n dx. So, here when we put 0, sin 0 is 0, and then sin this minus pi is also 0. So, this is 0, and then we have 1 over pi. Here again we have this term 0, and we will get this 1 over n square and cos n x. I would minus, this minus will be plus, and we have 0 to pi. So, we have n square pi, and then the cos pi, that is minus 1 n and minus 1. So, this is 0 when n is even, and minus 2 over n square pi if n is odd. So, similarly, we can get this b n, which is 1 over pi and minus pi to pi f x sin n x dx. This is 1 over n, and I skip all these calculations. So, we will get 2 and minus 1 over n. So, in this case we have minus 1 over n when n is even, and 3 over n if n is odd. So, our Fourier series representation for this function a 0 by 2, a 0 was minus pi by 2. So, we have minus pi by 4 minus, and that is a n and b n. So, we will get finally this cos x plus cos 3 x 3 square plus cos 5 x over 5 square and so on, plus for the sine we will get 3 over, that is b n. So, 3 over was 3 and sine x, we will get then the next term will be sine 2 x over 2, then 3 from here 3 sine 3 x over 3 and so on. Now, at x is equal to 0, what will be the sum of the series? So, the sum of the series at x is equal to 0. So, if we just see here, at x is equal to 0, we have to take the average of these two values, and that is 0 and minus pi and divide by 2. So, we have to take the f x, so at 0, 0 plus and f 0 minus divide by 2. So, we have 0 minus pi. So, we have minus pi by 2, and same at plus minus pi. So, at that plus minus pi we have again the pi and we have the minus pi. So, at these 2 points we have the plus pi and the minus pi by 2. So, will be 0. Okay, so, in this lecture we have seen the Fourier series and the conditions for the convergence, and that was the piecewise continuity and the differentiability of the function. Left and right derivative should exist, and more we will continue in the next lecture. Till then, bye. Thank you.